constants, right? So I just said, all right, let me just make this what I wish it was, and then just adjust it to make it back to what it should be. So I put minus 4x here to match this. Then I added x. Why did I add x? Because minus 4x plus x is minus 3x. And then I have a 3 here, but I need a 2, so I just subtract 1. So that's the same now, you agree? And now if I split this right here and do two integrals, what will that first integral be? It'll be 1, or I should say I do two fractions. So all that stuff over itself is 1, and then I have plus, then the other two pieces over this. If you did long division, you would get the exact same thing I just got there. The best chance you're going to have of this working is if the leading terms are the same, like 4x squared, or if this was like x cubed. They have to look pretty close to each other to make this work. All right, now you can integrate 1, yes? How about this? You don't have to do long division, right? So what do you see? This is linear over quadratic. How do you handle linear over quadratic? Pardon? Complete the square? Yes. I'll say yes and no. Yes and no? Here's what you don't do. All right? What you don't do is look at this and say, okay, I need to do partial fractions. Here's why you don't do that. If I were going to do partial fractions on this, then you would have to see if you can factor that. And that does not factor. So that's an irreducible quadratic. So what do we do with irreducible quadratics when it comes to partial fractions? We place it here, and then on the top, what do we put? Linear, right? ax plus b. So then we could go through the whole process, right, of trying to figure out what a and b are. But if we get a and b, isn't what's up here just going to be linear? And isn't that what I started with already? So I already had a linear over quadratic. Why would I go through the process of trying to turn it into a linear over quadratic? In fact, you would get a is 1, you get b is negative 1 if you did this. So this is a waste of time. That means there has to be another way of doing it. And that's where the linear over quadratic comes in. Now, if you don't remember how to do that, we did it. It was example 7. So if you look back in your notes at example 7, how we did this, we let u be the denominator. We took its derivative and got 8x minus 4. And that's where I put in all those zeros and turned the top into the bottom. Remember that? Well, it's in your notes. It's also on video. So, yeah, we did 8 over 8 on the outside. Then we added and subtracted something. And then we broke it apart. And then we had to do, one of them became an arctan. The other one was a natural log, right? So check. In other words, I'm not going to obviously go through that whole problem again. All right. How are y'all feeling? Just like anything else in this class, you're going to have to go do your homework and practice with it. But I'll say that we're officially done with this. Do you remember this problem on the test? Do you remember what the first step for this was? A u sub of u equals root x. There's a few problems at the end of this section that the book tells you, here's the problem, make this u sub first. It's towards the end of the section. And so that's what they're talking about. You're going to do that first, and then when you do it, it's going to turn into rational function.
That's the one where you gave out the hint.
Yeah, I gave out the hint. The homework assignment is there. 7 through 41 odd. Now don't pack up yet. I mean, I know y'all want to go. I do too, but you got to get your money's worth, right?
I sat there and never did this homework.
All right. I think we need some random useless information. Do y'all feel like we should do some random useless information? I think we should. There's enough engineering majors and computer science majors in here that this might be somewhat interesting to you. So let me see if I can remember this. Hold on. Everyone got that? All right. Let's see if I can make this make sense. I know it's not fair to make you sit here and watch me do something like this, but you know, 34.58. What does this mean in our number system? This means that we have, let's do a different number. Let's do 534 and let's do 581 over here. So what this means is we have 5 hundreds plus 3 tens plus 4 ones, right? Okay. Plus 5 tenths plus 8 100ths plus 1 1,000th. That makes sense? Okay. This means 5 10 squareds plus 3 10 to the firsts plus 4 10 to the zeros plus 5 10 to the negative ones plus 8 10 to the negative twos plus 1 10 to the negative 1. When you write a number down in our number system, pardon? Negative 3, I have no idea why I did that. When you write a number down in our number system, each space represents how many powers of 10, or so you have 4, and then what, powers of 10? This space means 10 to the first power, 10 squared, 10 to the third, 10 to the fourth, 10 to the fifth, 10 to the sixth, so on and so forth, right? Yeah? Then here, obviously the other way around. That's what base 10 numbers look like. The reason why we call it base 10 is because all of these are powers of 10, right? In base 10 number system, there are how many digits in a base 10 number system? 10. Here are the only digits we are allowed to use in a base 10 number system. Right? Those are the 10 numbers. If I combine those 10 numbers in any way, then it's going to be, I can expand it out like that. That's different than binary. In binary, there's only how many numbers? 2 numbers. You're only allowed to write 2 numbers in binary. So that's what I want to, this is really what I want to get at, is binary. In binary, which is what computers use, right? Zeros and ones. That's all you have, right? On or off. That's all a computer knows, on or off. So all numbers are comprised of zeros and ones. So in binary, if I write 1, 0, 1, 1, 0, 1, we can assume there's a decimal point there, right? So what does this first 1 mean? I have 1 times 2 to the first power instead of 10 to the first power. Hold on. 2 to the 0. This is ones. Yeah, 2 to the 0. Sorry. Plus, what about this one right here? 0 times 2 to the first. What about this one? 1, 2 to the second. Now this one. 1, 2 to the third. Yes?
Yes.
Okay, and then this last one, or no, we have a 0 now. 0, 2 to the fourth, and then the last one, 1, 2 to the fifth. Yes? Okay, so let's add these up. 2 to the 0, 2 to the 0 is 1, right? 1 times 1? 1. This is 1 plus, what's this? 0, right? What's this? 4 times 1, that's a 4. Here? 8 times 1, that's 8. So we have 8 here. And then here, nothing. And then here, 32. So 32 plus 8 plus 4 plus 1? 45. So this is the number 45. 101101 is the number 45. Got it? How many of you have seen that before?
Never seen that. Divide that by another binary.
Now, well, here's what not a lot of people have ever seen. What is this? 0.111 forever in binary. In binary. Now we know as in base 10, what does this mean? 0.111 forever. This is actually 1/9. If you don't believe it, just go do it. 1 divided by 9, or 9 divided, sorry, it's backwards. 1 divided by 9, right? So does 9 go into 1? No. So we put a 0. We go 1 time, then we put 9 here. We subtract, we get 1, drop a 0. Does 9 go in here? Yes, once. And we keep doing this. We get 1 forever. So in base 10, this is 1/9. Agreed? So what's this? Let's see. This is 1 times 2 to the negative 1. That's the first one, right? Plus, what's the next one? 1, 2 to the negative 2. Plus the next one. 1, 2 to the negative 3. See, I'm using base binary, right? So isn't everything base 2?
Yeah.
And then I keep going, right? Yeah? Okay. So if I write this out, isn't 2 to the negative 1 1 over 2? That's 1/2. What's this one? 1/4. What's this one? 1/8. What's this one? 1/16. Next one. And it goes forever. Right? Well, guess what that adds up to be, everyone? Any idea? We're going to study this later. It's called the geometric series. This adds up to be 1.
Because you cross out everything as it goes because it repeats itself.
Here, this is the best way I can explain that this is 1. If we say that 1 unit is from this wall to that wall, then let's talk about what this is. I walk, the first half means I go halfway, right? And then a fourth would mean a fourth of the room, which should put me here. And then an eighth of the room, which should put me here. And then a 16th, which should put me here. Understand? I'm halving it each time. And I do that. If I do that forever, theoretically, it approaches 1. The limit is 1. Okay? The reason why I'm showing this to you is if you really want to confuse somebody, you can ask someone, you can tell someone that this is true. Well, if you give that to someone and you say, is that correct? Is that true? And they say no, then you can argue that it is true. 1 in base 10 is equivalent to 0.111 forever in binary. We know that if we're looking at these as both base 10, then 1 is equal to 1/9. I'm sorry, me writing this down, right? Because that's what 1/9 is in base 10. This is obviously not true. So if you wrote this down on the board, people would think that's what you're saying. And they'd say you're crazy. But if that's a base 10 number and this is a binary number, then it's true. It's kind of weird. All right. Oh, I kept you over a minute. Where's the sign-in sheet? Got it? Anyone need it? Have a good weekend. Do your homework.
Does binary have an advantage over base 10?
The advantage to binary is